Okay, so in this study, we revised the calculation of genomic inbreeding in the US national evaluation. Specifically, we revised the scaling and the incorporation of the X chromosome information. We need to control inbreeding because it can affect the genetic progress of a population by increasing the prevalence of deleterious recessive alleles or by decreasing the overall profitability through inbreeding depressions. For many decades, breeders used pedigrees in an attempt to control inbreeding, but genomic measures of relationship can provide more precise control. To measure and control inbreeding, relationships of each animal with the existing population are calculated when the genotype arrives, and then they are recalculated monthly because new ancestors might have been added to the database or changed, or even new higher density genotypes could have been included in the reference population. And because genotypes are not always available for all animals, we need methods to make the genomic relationship matrix to match the pedigree matrix, and this correlation between G and A is strongly dependent on the use of different allele frequencies to compute the relationships. Genomic inbreeding estimates computed using 0.5 or base population allele frequencies are highly correlated for some breeds but not for others. A frequency of 0.5 has been used for reported genomic inbreeding in the US since 2010 because the method to compute base population frequencies became unaffordable for the population size. Therefore, new testing for assigning allele frequencies was needed. Most of the method ignores the X chromosome when estimating relationship between males and females because the inheritance pattern of the X is different between them. For example, if you have a sire X chromosome that is inherited by his daughters but not his sons, so relationships differ for full brothers compared with full sisters. To avoid these issues, most evaluations simply excluded the X chromosome, but in mating programs this can increase daughter inbreeding when two parents have the same X chromosome. And because marker density on the X chromosome is low on commercial chips, the effect on the accuracy of genomic prediction is almost zero. However, pedigree and genomic relationships can both account for the X chromosome, which is relevant for mating programs. So the aims of this study were, one, to evaluate the impact of allele frequency on genomic inbreeding computation. Second, to adjust for the X chromosome to better account for differences between males and females and improve in that way the scaling of the genomic to pedigree inbreeding. And after the writing of this abstract, a third objective was added, and it was to improve the computational efficiency of the whole system. The scaling of G to A uses the diagonal and off-diagonal of the G matrix among bulls. So we needed to add a constant to the G diagonal for females and multiply the off-diagonal for males with females and females with females by another constant. Currently, we use SNPs across the whole genome, including those in the pseudo-autosomal region and those in the remaining part of the X chromosome. So those more than 2,000 markers on the X are roughly 3% of the 80K markers that currently used. So in equation 1, this is the adjustment for females, and in equation 2, I'm showing the adjustment for a female or male-female off diagonals. We also calculated haplotype inbreeding using a subroutine that was implemented in the improved version of the program FixPet. The calculations were compared using the National Cooperator Database of the CDCB, and those were more than 3.5 million genotyped animals and 80 million records in the pedigree file of December 2020. The number of animals by breed and sex are shown in this table, and the genotypes for all animals came from 44 different chips that had been previously imputed to 80K using the FindUp version 3. In this plot, we can see the inbreeding trends across breed by year of birth. All the inbreeding measurements have been consistently increasing across time. The inbreeding yearly increase over the past 30 years for genomic and pedigree was around 4 percentage points for both pedigree and genomic inbreeding. For animals born between 1999 and 2009, the average inbreeding increase was around 2.4 for pedigree and 1.6 for genomic. But moving to animals born between 2010 and 2020, the increases were higher, around 4% for pedigree and 5% points for genomic inbreeding. The pedigree, genomic, haplotype-based, and expected future inbreeding were estimated after the X chromosome corrections for all purebred genotyped animals. In this table, we have the mean, minimums, and maximum across breeds estimated separately for females and males. The average differences between male and female genomic inbreeding was 0.9, and the difference in haplotype inbreeding was 0.7 after we applied the X chromosome adjustments. Here we have different inbreeding values estimated by breed. So the blue bars are representing pedigree, and the orange bars and gray are genomic and haplotype inbreeding. The Jerseys had the highest pedigree inbreeding, followed by Holstein, and last, the Brown Swiss had the lowest value. On the genomic inbreeding, Holstein were the highest, followed by Jerseys, and lastly, Ayrshires had the lowest values. And for haplotype inbreeding, Jerseys were the highest, followed by Brown Swiss, and the lowest again for Ayrshires. In this table, I'm showing the effects of different allele frequencies on inbreeding calculations. These were restricted to animals with no heterosis and more than 90% pedigree completeness. So the inbreeding coefficients were pedigree inbreeding, genomic inbreeding using 0.5 or base population frequencies, genomic inbreeding using 0.5 and the X chromosome adjustment, and haplotype-based inbreeding. And below we have the estimated future inbreeding was also computed on 0.5 or base population allele frequencies and 0.5 plus the X correction. The differences in mean genomic inbreeding between sexes obviously were smaller after we applied the X chromosome adjustment for all breeds except for Brown Swiss. This table shows the correlations across breeds and sexes for the different inbreeding definitions. Breeds with smaller populations, such as Ayrshires and Guernseys, were more sensitive to the use of different allele frequencies. Correlations with pedigree inbreeding were generally higher using 0.5 or 0.5 plus the X correction when we compare them with the base population allele frequency. And the average correlations across breeds were 0.67 for 0.5 and 0.5 plus the X corrected, and only 0.54 for base allele frequencies. Correlations with pedigree EFI were similar using either 0.5 or base population or the X corrected EFI, and were all around 0.84. The correlations between haplotype and pedigree inbreeding were not higher compared with the rest of the genomic inbreeding values that we compute. So in agreement with some previous studies, the correlations among pedigree and genomic inbreeding were higher for most breeds using 0.5 instead of the base population allele frequencies. Correlations with genomic EFI with pedigree EFI tended to be higher using the base population frequencies instead. The haplotype inbreeding had lower correlations with pedigree inbreeding than using the 0.5 allele frequency. The X chromosome corrections allow the average differences between male and female to be smaller, and therefore the genomic inbreeding more similar to pedigree inbreeding, although some of these differences will never completely disappear because male genetics in dairy cattle, especially in Holstein, is limited to a few ancestors only. Also, the correction for the X chromosome contribution eliminated the differences within full C families. Another product of the research was not included at the time of submitting, as I said before, but is included in a submitted manuscript, and it was the improvement of computational efficiency that was done by Gerald Jensen from CDCB, and it was mainly because the new computation is done in parallel processing. So about that, the efficiency of the computation was greatly improved, and the new programs and adjustments were implemented in the national evaluation in April this year. Finally, we can conclude that the genomic measures of relationship and inbreeding are different for males and female, that the adjustments to the scale of genomic measures to map the pedigree relationships were successfully applied, and to the whole national evaluation. Adjusting pedigree relationship for variation on the X chromosome is feasible, but the acceptance of this approach might require more education for the general public. Inbreeding calculation from haplotypes did not give higher correlations with pedigree inbreeding than using inbreeding calculated from the G matrix. Finally, the improvements in computation efficiency resulted in rapid calculations, allowing more frequent updates to account for changing pedigrees and genotypes. So with that, I would like to thank the data providers and the funding, and I will be happy to answer your questions. Thank you.